Hello. In this module, we are going to cover one of the most fundamental concepts of thermodynamics, namely energy, heat, and work. In case this module becomes too long, I'll concentrate on just energy here and probably talk about heat and work in the next submodule. So let's get started with what we mean by energy. Even before going into the meaning of energy, let's first talk about a system. It's a very fundamental concept of thermodynamics. What is a system? Simply put, it means anything with a boundary is called a system. You can run your imagination. Just think of a turbine, pump, your coffee mug in front of you, your computer, even a human being. Anything can be a system, even vacuum where there is nothing inside. The boundary can be a physical boundary, it could be a totally imaginary boundary. Anything outside the system is called the surroundings. Well, before discussing energy, let's start with even simpler concept. So the system, any system will have a certain mass, and the mass is represented by the symbol m. Is called mass, expressed in SI unit, always in kg. So typical mass of a big 18-wheelers is probably fully loaded is 80,000 pounds. And you can convert that into kilograms. It will be probably a huge amount. Well, 1 pound, 2.2 pounds is 1 kg. So you can do your math and find out how much that is. So this is a large engineering system. So I was talking about that because when we try to understand energy, we'll use this 18-wheeler as an example. I don't want to go into a big discussion of mass. Just I leave it as your homework to go read the book and try to appreciate what mass is, even though it's a simple concept. So wherever there is mass, there is energy. Okay, first thing first, let's look at all the symbols used. Energy E is the symbol. It's called the stored energy, or simply energy. And it's given in the unit of kilojoule. In mechanics, you must have learned the unit to be joule. We'll use kilojoule. One related variable is specific energy. E is called capital E by M, specific stored energy, and its unit is kilojoule per kg. So as you can see, wherever there is mass, there is energy. So if you know the energy per unit mass, then the total stored energy is given by mass times small e. Okay, so we haven't understood any meaning yet. It's just simple symbols. And let's now expand on what we mean by energy. Well, even before that, let me just first write down an operational definition. By that I mean pure formula. You're going to memorize this. What is energy? It is Ke plus Pe plus Eu. Nothing else exists. Let people not confuse you by saying, where is your thermal energy? Where is the kinetic? Where is the nuclear energy? Which term represents a chemical energy? You just simply memorize this as energies. All kinds of energies built in here. Ke plus Pe plus Eu. Okay. So to understand energy, I assert that if you understand kinetic energy well, then you can understand all kinds of energy. Okay? So let's go one by one. So let's say we want to understand what is kinetic energy. Everybody knows its definition again, one more time, half mv squared, but that will produce joule, if you recall. So we will make a habit of writing the formula in this manner. We'll divide by 2000, then the unit will become kilojoule all the time. Well, so what do you mean by kinetic energy? If you go to mechanics, you will find that in mechanics, many people will define kinetic energy as ability of a body to do work. then you have to define what is work. So that's kind of the traditional definition of kinetic energy. So for instance, this is the constructive definition of kinetic energy, that this kinetic energy from this arrow is being converted, is pulling something up. And that's the typical definition of kinetic energy in mechanics. We'll look at it slightly differently. We will look into kinetic energy and we'll assert that it's a destructive capacity of a system. Here the arrow has a lot of kinetic energy, and because of that, it is cracking this block. Well, it might seem very intuitive, and everybody say, yeah, I agree with that. What is the big deal? Well, it was a big deal because before, when Newton came up with the idea of momentum, everybody thought that if somebody gave the same problem to Newton, that this arrow is hitting this block, and the destruction in the block, will that be proportional to the mass of the arrow? Newton would say yes. How about the velocity? He will say yes, it will go with momentum, m times v. At that time, every scientist, every engineer agreed with that. Except one lady, her name was Émilie du Châtelet, a French lady. She was translating Principia in French. Very big physicist on her own. But at that time, if you're a girl, nobody takes you seriously. All right. So what happened was she was doing some experiment. She was dropping, actually her experiment was quite simple. She was dropping some bearing ball on some, mud or clay. And she was noticing, at that time she couldn't figure out exactly what velocity the ball is going to hit the mud with. And she was looking at the area of destruction. So she expected the area should be proportional to velocity because momentum goes with velocity, area of destruction. To her surprise, she found the graph goes like this, not linear. It's not proportional to velocity. When she showed that result to other scientists, they said, no, you must have made a mistake. It should be a straight line because destruction goes with velocity. She's the first person who said, no, the destruction goes with velocity square. And the concept of kinetic energy was born. Only today we are giving her credit for coming up with this most important concept. So yes, mass time velocity, momentum is very important. When you analyze forces, you will find momentum everywhere. When you deal with energy, you will find kinetic energy will appear everywhere. And I'll make that case in a minute. But before that, some benchmark numbers so that you don't forget. I collected two examples in this animation. You can see that a 1 kg mass moving at 100 miles per hour, approximately a kinetic energy of 1 kilojoule. A better example in my mind is a 40-ton truck. This is the maximum weight of an 18-wheeler truck that you see in the freeway, traveling at 75 miles per hour. It will have about 20 million joules of kinetic energy. Well, you can use the unit converter anytime to figure out. So let me just show you where you can find the unit converter if you want to do this kind of calculation. You go to test, and right here you can click on the unit converter right on the main page and say you want to convert, let's say, the velocity, 75 miles per hour, or speed or velocity. Then you can just say 75. Type in 75 and you choose mile per hour. You'll find here all kinds of units, and that's about 33.5 meter per second. And this is a typical, it's 80-ton truck, maximum weight. So you go to mass, convert the mass. Where is that? Here's mass. If it's a 40. How much was that? 80-ton truck. 80 ton into kg. Oh, so sorry. It's a 40-ton truck. That's the maximum weight. I was mistaken. So it would be 36,000 kg. So 40-ton truck is the maximum mass of a truck. So you get some benchmark number. Sorry, go back to animations. So you get some benchmark number of kinetic energy, which is about 20 million joules. If you go and convert that into no, what about potential energy? Potential energy, again, we are all familiar from mechanics, and if you do the math, you'll find if the, going back to the truck example, suppose we take the truck in the freeway in a ramp, and that's where it stops. So if it goes up and stops there, so what is that height? So that will give you some benchmark. So if you just do the kinetic energy is converted to potential energy, you can come up with a very simple formula: half mv square equals mgz. Well, so that will give you z being the height. How much that is? That, I think that comes out to be about 56 meter. Please check. I just quickly did that on the side. So the potential energy formula really is given by PE is mgz divided by 1000 kilojoule. See, we are not using mgh. You're familiar with mgh because h is reserved for enthalpy in thermodynamics. Also, I'm dividing by 1000 so that my unit is always kilojoule. So that brings us to the last part. So stored energy is what? Ke plus Pe plus Eu. So what is Eu? Again, I'll try to explain that using an animation. I would suggest you go through each of these animations. That will really help you. Okay, simply put, if you think of the system, ultimately it's made of molecules. In this case, this is a rendition, a cartoon of a solid, and the solid molecules basically vibrates like this. And as you can see, when they vibrate, they have some kinetic energy. And that kinetic energy is reflected in its temperature. When you touch, suppose you touch this solid, if it's hotter, these molecules will vibrate faster and they will hit your fingertips faster. They will transfer more energy into your neurons and you will say, oh, this is hot. In fact, if it is very, very hot, you know that your finger can burn. Why? Think about it. It's those molecules hitting your skin so much that they're damaging your skin. And that's called burning. Well, for solid, it's only the vibration. For a gas, for instance, it can be complicated. It could be a combination of kinetic energy, of vibration, kinetic energy of rotation, and translation, and all together, all these things are combined. But it turns out that for gas, the translational kinetic energy reflects the temperature. Anyway, but I'm going into area which we don't have to really cover, but it's good to know. So what is the internal energy then? It's essentially reflected by the temperature, mostly by the temperature of the substance, and it's the reflection of the kinetic energy of the molecules, kinetic energy and potential energy of the molecules. Well, the potential energy part I haven't covered here, but you can understand that for a system, when there are molecules, they can have potential energy. Let me just quickly explain what I mean by that. To understand that, let's go back to this potential energy first. What is this PE? You recall, we already know the formula. It is mgz over 1000, right? That's our operational definition. So when you take a mass on Earth and suppose it's at a certain height z, so where does this energy reside? Think for a second. If I say, here is a mass up here compared to a mass up there, everyone will say that, oh, this will have more. Suppose this is at height z1 and this is at height z2, and z2 being bigger than z1, you will say this has more potential energy. Now, if you do a chemical test on these two bodies, they're identical, suppose they're two baseballs, then you will say there is nothing different between them. So where is the energy stored? Kinetic energy is very clear. It's stored in the velocity square, right? M times velocity square. PE is stored where? Well, it is stored this is gravitational potential energy. You can think gravity in like as if an invisible spring is connecting, a linear spring connecting. And in that case, it's very clear over here the spring is elongated more, so you can say, oh, there is more energy there. So really the energy is stored in the gravitational field, which is invisible. The reason I'm mentioning this is that whenever any body is pulled by a force, whether it may not be moving, it can be standing, but it's pulled or pushed, that dynamic balance, that balance will always make sure you can think like there are invisible springs they're taught. So when I say kinetic energy and potential energy of molecule, Ke and Pe of molecules, excuse me, I should use capital here. What do I mean? Kinetic energy you already understood from the animation. And what is the potential energy? The potential energy comes from the fact that all these molecules are attracted to each other. Think about it. There must be some force, molecular, intermolecular force. Otherwise, the molecules will go everywhere, right? In case of a solid, it will be very, very strong. So you have to overcome that for a solid to become liquid. So in liquid, what will happen? The spring has been extended so much, it's almost broken. In a gas, it's completely broken. So you can think an analogy like if I take this mass and take it out of Earth all the way to space, when a solid becomes a gas, it's something like that. The molecules can go anywhere they want. Wherever you put them, the molecules will occupy that volume. So it's understandable that the potential energy of the molecules in a gaseous phase will be higher than in the liquid phase or solid phase. So temperature is one of the reflections. That's the kinetic energy of the molecules reflects on temperature, and potential energy of molecules is reflected in the phase. So for instance, if I have liquid water versus ice at the same temperature, you can bet that the liquid water will have more molecular potential energy and hence more stored energy. So I hope I have explained to you what kinetic energy is, and I have also explained what potential energy is. But why am I saying the meaning of it can be derived from kinetic energy? So the idea is that if you see anything has a potential energy, essentially that energy can be very easily converted into kinetic energy. Correct? I mean, if I have this body up there, all I can do is to leave it and it will fall down and it will convert into kinetic energy. And we have this intuitive sense. So when you see a big rock on the top of a hill and you drive past that hill, you are always wondering, hey, if in case it rolls down. So it has this potential to do damage. So therefore, I like the term potential energy from that perspective. So to summarize, what is stored energy? It is sum of kinetic, potential, and internal energy. Kinetic energy is something, it's given by mv squared by 2000, so many kilojoules, reflected in the velocity. The higher the velocity square, the higher the kinetic energy. And what is potential energy? When, because of a force field, a system has a lot of energy that can suddenly convert itself to kinetic energy and do the damage, then it is called the potential energy. And it's given by this formula, mgz over 1000, where g is approximately, about 10 meter per second square. And the internal energy, U, capital U, is the kinetic and potential energy of the molecules, the random energy. So this random energy are reflected, the kinetic energy is reflected in the temperature and the phase of the system. So if it's liquid versus solid, etc. So the rule of thumb is energy will go up if velocity goes up, energy will go up if height goes up. These are kinetic and potential energy. These are called macroscopic kinetic and potential energy. We can see that with our naked eye. And EU is the internal energy because we don't see with our naked eye. And these are the molecular energy, in that sense, energy of the molecules, which are reflected in the temperature and phase. To summarize, I'll take you back to an animation which will explain what is stored energy, the same formula, and the total energy is reflected in this bar where there are different components of the energy, as you can see. So the internal energy in this case is being reflected by the temperature of the molecules. The kinetic energy is, of course, you can see that if a force pushes, the kinetic energy is increasing here. And potential energy, when I lift something, is potential energy is increasing. So I'll stop here and we'll look into how heat and work, which many confuse with energy, cannot be just said energy, because see, we have just defined what is stored energy without ever mentioning heat or work.